In this video, we'll be teaching you how to do vector addition and subtraction on the Argand diagram. The skill you learn in this video can be applied whenever vectors are used, including in physics and in other areas of maths. Now, addition, there are two methods. The first method, and the most commonly accepted method, is called the parallelogram method. Now, as the name suggests, we are going to draw a parallelogram based on the two vectors given to us. Now, the most important thing to start off with is to understand how exams will actually describe vectors to you. So the exam would say that the vector represented by the point A from the origin. Now, a shorthand for this will be OA with an arrow on the top. And we will call this Z1. Sometimes they might give you other lowercase letters, but in this case we'll call it Z1. Now, similarly, OB, the vector OB, be Z2. As you can see, OA and OB, the letters, the order in which these letters are given is very important because it shows you that you're going in that direction, from O to A and from O to B. In order to find the parallelogram, we look at OA and OB and we attempt to draw a parallelogram from it, like this. And we'll call that point, let's say, C. Now, the sum of these vectors is the one end from the parallelogram where the two vectors began to the other end of the parallelogram. So we simply have to join O to C, and that will be the vector Z1 plus Z2. Okay, and on paper you would write it like this: OC equals to Z1 plus Z2. And that's how this vector is represented on the Argand diagram. Now, let's say over here we're interested in subtracting Z1 and Z2. Okay, given the same vectors. Now, according to the parallelogram method, if we're trying to do Z1 minus Z2, we're really trying to do Z1 plus the negative version of Z2. So to describe what the negative version of Z2 is, we reverse the direction. So instead of having OB, we're going to have BO, because BO is negative Z2. Now, the way to draw BO is that because the parallelogram must have one of its vertices starting in the same spot, and we're going to actually draw a new version of BO. So instead of taking this and just putting the arrow at the end there, what we're going to do is we're going to draw BO like this. Okay, as you can see, instead of going OB, we have this thing. So this will be minus Z2. Now, you wouldn't label this B because that's B. Okay, that could be B dash. So you can distinguish that these are two different points, but the vector, obviously going in this other direction, still the same modulus, still the same length, is minus Z2. Now, again, we draw the parallelogram. And our vector starts from where the parallelogram was made, the origin, to the other end. So this vector is going to be Z1 minus Z2. The second method of vector addition and subtraction is the head-to-tail method. There are advantages to this method in the sense that you can more easily visualize it as a sort of a journey, okay, where you begin at one point and you end at the other. So if we're going to do this again, let's use different letters. Let's say this is D and this is E. So we can say Z3 is equal to the vector from O to D, and Z4 is the vector from O to E. So Z3, Z4. So if you want to create Z3 plus Z4, what you can do is, we know that vectors are the same no matter where you translate them on the Argand diagram. So we're going to take this vector and we're going to translate it up here. Obviously keeping the length the same. So that's also Z4 because they are the same vector. I mean, they have the same length and they have the same direction. As you can see, now all we have to do is just block out this part. We don't need it anymore. And let's just focus on Z3 plus Z4. Now, according to this head-to-tail method, we go from 0, the origin, where the first vector began, Z3. We go to its end, see where the head is, the arrow, and we connect it to the tail of Z4 and continue along Z4 to finally get there. So the overall journey, the overall effect of this is that we've gone from O to this new point, let's call it F, and this will be the vector Z3 plus Z4. As you can see, it's not too different from drawing a parallelogram if we ended up drawing a parallelogram from E to F. Now, subtraction, this is where the head-to-tail method stands out a little bit. Again, we're going to have Z3 and Z4 as the same as before. But we're also going to have, what we're going to do is we're going to do Z3 minus Z4. Now, to get minus Z4, what we're going to do is we're going to reverse this 0e. So instead of having 0e, we're going to have EO instead, like this. So from here to there. So we're going to draw the arrow at the other end. Okay, it's almost like we've just removed this arrow and brought the arrow back here. Again, with the head-to-toe method, this time we're actually starting from here. This is the starting point. We follow it along the vector, we end at the origin, we continue along Z3, and we end at D. So the overall journey was from E to O, like this. Now, this is Z3 minus Z4. The only thing that you'll find an issue with this subtraction is that this Z3 minus Z4 is not starting at the origin. So what we can actually do is we can just bring it back here. We can draw the same vector over here if you are interested in having the same vector of Z3 minus Z4 but starting at the origin. And as you can see, that has the purpose of finding what coordinate it will lead you to from the origin. These two are the same vectors. Again, this could have been done with a parallelogram. As an exercise, why don't you attempt to subtract these two vectors like I've done here using the parallelogram for these two vectors. Alright, over in this triangle, notice how the question we've intentionally obstructed these coordinates. So again, I want you to focus on the fact that these are vectors and not coordinates. I mean, sure, if we know what coordinates A and B are, we can operate in terms of numbers, but in exams, you'll most likely be asked to operate in terms of just simple vectors, letters representing vectors. So the question is asking you to, obviously, the vector OA is given by you, so labeling with arrows as usual, and OB is the vector V. Okay. Express vector A to B in terms of U and V. Now, I want to sort of emphasize the importance of doing the head-to-tail method for this, because as soon as you realize that you want to go from A to B, you want to start from here and you want to end up over here. What you're really doing is you're going from here to the origin first, then from the origin to B. So the key here is to be able to reverse this, and this thing is minus U. So the answer to this question will be the vector AB from A to B is minus U plus V, or you can say it's V minus U. Now, you might sort of be getting the hang of this from the earlier question that it seems like whenever you have a minus complex vector, you're sort of like starting from where that vector is represented as a coordinate. As you can see, if we're doing minus u, we're going to start there. Okay, if we had another point somewhere else and we're going to minus that one, we're going to start there. Okay, ultimately our vector is from A to B. Okay, and that was v minus u, as we found. Now, what conditions must u and v satisfy so that triangle OAB is isosceles and the vector AB is real? Now, u and v, for them to actually be make an isosceles triangle, clearly the length of u, which we write as this sort of absolute value sign, which we'll discuss later, it's called the modulus, they must also they'll be equal in length. So these rays must be equal in length, clearly, for an isosceles triangle. But what's more is that we need to somehow have a way to explain how we can make AB real. Now, in terms of real, this actually means that AB, the vector, is exactly horizontal. Okay, it doesn't have any sort of vertical components, which is why it's real. Okay, to actually prove that, we must somehow notice that geometrically, okay, if that's horizontal, then there's something to do with these angles being the same, and there are ways to deal with that as well, dealing with the argument of u equals to pi minus the argument of v. Sorry, the argument of u, the argument of v. And we will be learning that in the next chapter.